Yeah, when you're ready. Yeah, hi everybody. So thank you for being here, first of all. So yeah, what I'm going to be talking about is ultra high energy neutrinos. So obviously there's going to be some overlap with what Walter has been talking about this morning, but I'll try to be brief on what he has already talked about. And I think I will just start with a basic question to which you probably already know the answer at this point, which is what are ultra high energy neutrinos? And this question is intrinsically connected to the question of how do we detect them, because as we will see, the main barrier that we have at this point between high energy and ultra high energy neutrino is a practical one. IceCube has not been able to observe neutrinos above a certain energy. So this is an important question for us. And I will try to close this first part of the talk with somewhat more general question, which is why are they relevant for physics as a whole? What can we actually learn from ultra high energy, from a measurement of the ultra high energy neutrinos that we don't know yet? And this will more or less close the first part of my talk. And then in the second part of my talk, I will actually talk about something more practical, which is assuming that at some point, hopefully not too late, we will be able to measure ultra high energy neutrinos. How can we actually squeeze information out of these neutrinos to learn something from them? So this will be more of let's say, I would try to phrase the discussion in terms of what are the observables of ultra high energy neutrinos that we don't have available because we have no measurement, but we might have available. So I would try to phrase this in terms of what can we gain from knowing the energy spectrum, the arrival direction, and possibly field composition, although I will not manage to get to the part of these ultra high energy neutrinos. So starting with the first question, what are ultra high energy neutrinos? Of course, we have to start with the multi-messenger picture that at this point I think is very familiar to everybody. Neutrino astrophysics was born because people wanted to try to have a different view of the sources of cosmic rays. That's because cosmic rays do not point back to sources, as you know. And IceCube succeeded in this respect. It was quite clear already in the 90s that if you want to detect a neutrino flux of the order of magnitude of the ultra energy cosmic ray flux, so assuming that they are comparable, you would need a detector of the size, of a typical size of 1 kilometer cube. And by going in this direction, IceCube was able to measure this neutrino flux in the range between 10 TeV and 10 PeV, more or less. Here is where the last measure ends, and it's more or less 10 PeV. So this is a picture that you've already seen. This is the multi-messenger flux of gamma rays, neutrinos, and ultra-energy cosmic rays as a function of the energy. And it's already clear because you've already seen this similar picture in Walter's slides this morning. There's an empty window here, which is the window of the so-called ultra-high energy neutrinos. The neutrinos are above 10 PeV. Up until now, we have all the upper bounds. These are the upper bounds by IceCube. There are some other upper bounds by Auger, which also has not been able to observe anything, but there is no measurement. So this is essentially an unexplored territory. And why this territory would be interesting to explore, I think it boils down to a simple estimate in reality. As you have seen already during Walter's lecture, when a neutrino is produced by a collision of cosmic rays, say with gamma, with photons, or with the target protons, the typical energy that the neutrino carry is something like 5% of the parent proton energy. So that means that the IceCube neutrino that we are seeing here are typically produced by cosmic rays here at about maybe 1 eV, but not higher. So the very tail end of the cosmic ray spectrum, the very mostly energetic ultra energy cosmic rays would actually produce neutrinos with typical energies 1 eV or higher, which are just in the window in which we have no measurement. So if we want to have a smoking gun signature of the presence of ultra high energy cosmic rays in the very tail end of the spectrum, we need to measure ultra high energy neutrino flux, which we haven't yet. Now, what are the mechanisms by which neutrinos can be produced in this energy window? One well-known mechanism, which you have already discussed this morning, and which actually historically was the first one to be thought of even before IceCube was a thing, is just cosmogenic neutrinos. The reason why historically this was the first mechanism to be thought of is that it requires only ingredients that are known to exist with a lot of certainty. One is cosmic rays. We know that cosmic rays exist. One is cosmic microwave background. We also know that that exists. And so because of the collision with cosmic rays and cosmic microwave background, neutrino production is unavoidable because of the pion production, which then decay into neutrinos. Of course, in order for this process to happen, one needs to meet the kinematical requirement, which is that the center of mass energy of the collision is large enough for pion production in the final state. And because of this, Greisen, Tzepin, and Kuzmin realized that this process would be of interest for the very ultra high energy cosmic rays. That means essentially above, so let's say 50 eV. That was the original estimate. they realized that above this energy, there was a mean free path for a proton-photon scattering of about 150 megaparsec. So in these collisions, neutrino production will be unavoidable. So in this sense, cosmogenic neutrinos are a guaranteed signal in the ultra-high energy range. However, even though they are a guaranteed signal, the magnitude of the signal that is expected is pretty much uncertain at this moment. And there are two main reasons for that. One is the uncertainty related to chemical composition, because heavy nuclei have a lower energy per nucleon, assuming the same cosmic ray energy, and therefore they have a hard time meeting this kinematic requirement, and that is the reason why typically heavy nuclei are less efficient in producing ultra-high energy neutrinos. The second reason is the high redshift behavior. As I've mentioned, there is this horizon of about 150 megaparsec, beyond which cosmic rays are not able to reach Earth just because of this process. So that means that cosmic rays are very weakly sensitive to the high redshift behavior of the sources of cosmic rays. This was something that also Walter was emphasizing this morning. On the other hand, neutrinos are essentially the sky is transparent to neutrinos. So they are sensitive to the high redshift behavior. So we don't know how large the cosmogenic neutrino flux is because we don't know how the cosmic ray sources are distributed at high redshifts. Now, besides cosmogenic neutrinos, another possible source of ultra-high energy neutrinos are simply sources of ultra-high energy cosmic rays. This is a somewhat model-dependent statement. If you want to have a source that produces ultra-high energy neutrinos inside the source, it means that there must be a sufficiently dense target, whether it's photons or whether it's protons, but there must be a target in the source, and there's no way that we can make this statement in general. So it's a model-dependent statement, obviously. But there are various models of sources. Some of them you've already seen them about tidal disruption events and gamma ray bursts. There are also other models related, for example, to newborn pulsars or blazars in which this requirement can be met. I also want to emphasize something. The requirement to have an ultra-high energy neutrino source, an efficient ultra-high energy neutrino source, is not necessarily the same as to have an ultra-high energy cosmic ray efficient source. In fact, if you think about it, it's kind of a complementary requirement. If you want to have an ultra-high energy neutrino source, you need to have a dense target. If you have a dense target, cosmic rays have a hard time escaping. So they kind of go in opposite directions. There are certain sources in which you can meet both requirements. So you can have a source that is efficient both in producing cosmic rays and neutrinos. There are others for which you can't. I just wanted to show one example. This is actually from Walter's group. These are where the production of ultra-high energy neutrinos and cosmic rays was studied in blazars, in different classes of blazars. And what they found was that the very brightest blazars, flat spectrum radio pulsars in particular, where am I here? Yeah, flat spectrum radio pulsars, because they are very bright, they have a lot of photon targets, and therefore they are very efficient in producing ultra-high energy neutrinos. So the neutrino flux, which is shown in this panel, is dominated by this flat spectrum radio pulsar contribution and is particularly large. But the corresponding contribution to cosmic ray flux, which is shown in the left panel, is subdominant. On the other hand, low luminosity BLX, which on the contrary do not have a very bright target photon density, they have just the opposite property. They are very efficient cosmic ray emitters, which can actually fit the tail of the cosmic ray spectrum, but the contribution to the neutrino flux is subdominant. It's mostly cosmogenic and is subdominant. So this is also another, this example is also interesting in another respect. You can actually see that source neutrinos can completely outshine the cosmogenic neutrinos, this particular example. So at this point, we cannot take anything for granted. The sky could be dominated by cosmogenic or source neutrinos. We just have no idea at present, I would say. So the second topic was about detection. How do we expect to detect ultra-high energy neutrinos? And this started, of course, with the ASCII. How have we detected the high energy neutrinos in the ASCII range? You already noticed, so I will go very fast. The idea is that neutrino scatters off the nucleons, it produces a cascade. The charged particles in the cascade produce optical photons by Cherenkov flight. Now, what is the limitation of this approach? The limitation is that optical photons are typically attenuated over a distance of about 100 meters. So if you want to have efficient detection, you need to instrument with photodetectors every 100 meters, which for a volume of 1 kilometer cube was accomplished, but going beyond that is probably going to be impossible. You cannot instrument a very huge volume with such a dense amount of photodetectors. But the idea to go beyond this is that in reality, a cascade at such ultra high energy can also produce a radio signal. I have some backup slides if you're interested. For now, let's just take for granted that this cascade can produce also a radio signal, the so-called Ascarian effect. Why radio signal is interesting for us? Because radio signal have a large wavelength, therefore they do not see obstacles and they're attenuated over much longer length. So typically of the order of 1 kilometer. So we don't need a very dense photodetector array. We just need a sparse array of radio antennas. This kind of array is planned or under construction at a few sites like Hara, Ariana, and RNOG. The one I will focus on mostly during this talk is the radio array that is planned to be built at ASCII 2 in the decade of 2030. So this will be an array with a sensitivity to a flux, which is essentially 10 to the minus 9, 10 to the minus 10 GeV per square centimeter per second per stereo. So 1 to 2 order of magnitude more sensitive than ASCII in terms of its square time. There are other proposals, of course, besides the in-ice proposals. I will just mention the one that is proposed for giant radio array for neutrino detection. So this is the ground. In this case, the target for neutrino interaction is not ice, but is the entire atmosphere. The idea is that when neutrino enters the atmosphere, it can collide with the nuclei and produce a shower. So if you have an array of radio antennas, you can detect the radio waves produced by the signal, by the shower. Actually, the most significant channels for neutrino detection by ground does not come from neutrino interacting in the atmosphere, but actually come from neutrinos interacting in the rock. If neutrinos passes through a layer of rock which is not too thick, for example, through a mountain, tau neutrino have to specify, then it can collide and produce the corresponding tau lepton via charged nuclear interaction, and then the tau lepton can escape from the mountain, enter the atmosphere, and produce a shower in the atmosphere more efficiently than a neutrino because it is charged. So if you point the radio antennas to the mountain, you're able to detect this signal. And there is no way to confuse this with the background of cosmic rays because cosmic rays wouldn't pass through mountain, obviously. So actually, this should also ring a bell alert here. Obviously, this process is sensitive in some way to flavor because you're able to detect mostly tau neutrinos. So this process is going to give you some sensitivity to flavor. Okay, so I think that's. Sorry, to just click on the. No. Okay, thanks. Okay, so now I think I'll come to the bottom line of this first part of the talk. Why ultra-high energy neutrinos are interesting? There is one reason, there are two answers to this question, I would say. One is mostly astrophysical in nature. Ultra-high energy neutrinos, as I've already mentioned, are a smoking gun signature of the presence of ultra-high energy cosmic rays inside sources. They may not necessarily come from the same sources as the ultra-high energy cosmic rays that we observe at Earth, but for sure, they are a signature of their presence. And they are therefore able to test the behavior of sources at high redshift. They are able to test the composition of ultra-high energy cosmic rays in a complementary way to what we can do with direct cosmic ray detection. On the other end, there is a second answer to this question, which is more, let's say, it has more the nature of fundamental physics. If we manage to detect ultra-high energy neutrinos in the near future, these will be the highest energy neutrinos ever observed. That means that they are able to test beyond the standard model physics in the neutrino sector to a scale that is simply not reachable by any kind of terrestrial experiment. So this is a kind of complementary information that we can get from there. Okay, so now starts the second part of my talk. Let's assume that we are in a not far future, say 10 to 20 years from now. What can we learn from actual measurements of ultra-high energy neutrinos? The first thing that we don't have available now is the energy spectrum. And to show how much uncertain this is at present, so this figure comes from a paper by Mauritian collaborators. This is a collection of theoretical models of ultra-high energy neutrino production. This is flux, again, versus energy, and each of these colored curves correspond to a specific model of neutrino production. This is a collection of cosmogenic neutrinos, but also source models coming from many different sources, newborn pulsars, BLXs, also blazars. And I think the thing that is most striking at present in this figure is that it's completely confused in the sense that the curves span more than 2 orders of magnitude in normalization. We have no idea how large the flux is. You can compare this to have a reference with the sensitivity of ASCII Gen 2 radio array, which is here. You can see that there are some fluxes that are so much above the sensitivity that they would lead to something like 500 events in 10 years, which is a lot, much more than we have observed with ASCII. This is a possibility at present that we cannot exclude. On the other hand, some other fluxes are so low that they are practically unobservable even in 10 years. But we cannot predict what will be observed, and therefore the measurement will be very useful in discriminating among different models. On the other hand, I must also say that for example, the spectral shape of this model, some of these are cosmogenic, some of these are source neutrinos. I'm not aware at present of a simple observable associated to that could allow, for example, to discriminate unambiguously between cosmogenic origin or source origin. So how to make best use of the energy spectrum, I think there probably is still work to do in this direction. There is a second information that would come from measuring ultra-high energy neutrinos, which is their direction, their angular distribution in the sky. Of course, we expect these neutrinos to be produced outside of our galaxy, which means that we expect them to be isotropically distributed. But even if they are on average isotropic, they can still carry information if we see fluctuation. The most obvious example, if the sky is populated by source neutrinos, so neutrinos are produced in specific astrophysical sources, and if these sources are sufficiently bright, we can expect to see some clustering in the structure, in the angular structure of these neutrinos, because a bright source would produce an excessive event coming from a special direction, the direction of the source, what we will call a multiplet. So searches of multiplets would be a way to try to understand if the neutrinos are produced in sources or they are cosmogenic in nature. So in the rest of my talk, I will try to make use of this information to have a projection of whether it will be possible for ultra-high energy neutrino radio arrays to detect point sources. And I will focus most of the discussion on AstroGen2 radio array. So if you have questions, we can discuss also ground, but the rest of the discussion will be focused on radio array at AstroGen2. Okay. So if the neutrino sky, the ultra-high energy neutrino sky, is powered by individual sources, and these individual sources are sufficiently bright, then the sky map of the events expected to be observed at IceCube could look something like this. This was the simulation of the response of the detector to a specific population of very bright, very flat spectrum radio quasar. Now, the value may not necessarily be realistic. This was mostly for pedagogical purposes that we did this plot. But what we did was we tessellated the sky into pixels of a solid angle of 2 degrees and 2 degrees. The choice comes just from the resolution that is predicted to be the optimal one for this radio arrays at AstroGen2. And as you can see, the sky map looks mostly empty, except for a few pixels that have something like 4 to 6 events inside of them. Obviously, these pixels are simply the presence of a point source inside that particular pixel. So this is the kind of signature we are looking for. If we are able to see clustering of neutrinos on a small scale in a few pixels, they could be a signature of a point source in that particular direction. Obviously, not any multiplet is by itself a signature of a point source. We must keep in mind that even if the flux is completely featureless, there is no point source, it's just a completely isotropic featureless sky, you could still have fictitious clustering of neutrinos simply by Poisson fluctuation. Remember that we have tessellated the sky into something like 3,000 pixels. This was the number of pixels in the sky map that I just showed. And therefore, it's quite easy that in some of these pixels, there may be an upper fluctuation, which looks like a point source, but it's not a point source. This is what is typically called the Lucas-Roy effect. So we have to correct for this. And in order to correct for this, we need to know how many neutrinos are detected over all sky. So we need to know how large is the diffuse neutrino flux. For our purposes, the diffuse neutrino flux is acting as a background because it's completely isotropic. There are no point sources in it. So again, for our purposes, this is a background. And I have shown a few slides ago that we have no idea how large this is at present. The only thing we can make now are educated guesses about how large this could be. So what we did, for example, for this work, we tested a few different models of diffuse neutrino flux, which are shown here with these 3 colored curves. We called it a low, intermediate, and high background. Of course, what we call the low background is definitely not the lowest background you can think of. In reality, it could be unobservable. It could be down here, and we could just not be able to observe anything. But this was just to give some benchmark reference levels of how large the neutrino flux could be. And I will show results for the green curve, which is what we call the intermediate benchmark neutrino flux. So from now on, I will assume that the green curve is the real neutrino flux that exists in nature, and I will just proceed from there. So the question is, what are the properties of the source population in order for us to detect point sources? What properties should they have? At a qualitative level, this is kind of easy to grasp. If the sources are individually very bright, we expect them to, it's more likely that we can see point sources because they are bright individually, so it's easier for them to shine as individual sources. On the other hand, if the neutrino flux is produced by cosmogenic, for example, origin, or if they are produced by a population of very dim sources, a lot of very dim sources, This is just the contrary, right? You don't expect to see them as individually point sources. Now the question is, how do we quantify this statement? This is a qualitative statement, we now have to quantify it. The historical way to do this, and this has already been done for the ice cube energy range, so we simply transported this into the ultra high energy range, is by parameterizing the source population in terms of two main parameters. The number density of sources, which tells us how many sources are there per unit volume, and the individual luminosity of a single of these sources. Obviously, this simple parameterization, as you can expect, hides a lot of complexity behind it. For example, it is absolutely not necessarily true that all sources have the same luminosity. And also there is an assumption about how these sources are distributed in redshift. If these sources are closer to the Earth, it's going to be easier for us to detect them than if they are farther away from the Earth. Now, all of this is kind of washed out in this parameterization because it's just a simple way to understand the physics behind it. So this is the parameter space that we are looking at: luminosity of individual source and how many sources we have per unit volume, so the number density. And the first information that we can immediately draw is that the whole of the population of sources cannot exceed the diffuse neutrino flux that we have assumed by consistency, right? We have assumed the green model that I showed a moment ago, and the whole of the population cannot exceed that green flux. Now, the diffuse neutrino flux, as you know, is proportional to how many sources you have times how bright they are. So it's just proportional to the product of these two quantities. So this diagonal line that you can see here, this black line, corresponds to saturating the diffuse neutrino flux. Anything that is above this line would be inconsistent with our choice of the background of diffuse neutrino flux. So this is the first information that we can immediately draw. You can also see that on this plot, we showed a few sources, a few candidate sources. Now, this is obviously just a reference choice for this population. I mean, here we have something like luminosity AGN, VLux, and we have flat spectrum radio pulsars. Obviously, for all of these sources, the only thing that we know is the number density, because we see them in electromagnetic spectrum, so we know how many sources there are per unit volume. We have no idea what is their neutrino luminosity. So there is no way to know what is the horizontal coordinate of these sources. What we did here, as you can obviously notice on the figure, was just to put them on the line saturating the diffuse neutrino flux. So this is as bright as they could be without exceeding the diffuse neutrino flux that we have assumed. But it must be clear that we have no real idea where these sources would lie on the horizontal flux, because that is a model-dependent statement. Okay, so I think that comes to the final answer, to the final, let's say, to the answer to the original question that I was posing. What can we expect a detection of point sources from this population? To answer this question, what we do is, for each point of this parameter space, so for each choice of luminosity and number density, we simulate the response of ice cube to radio array in 10 years to try to see how many point sources we have detected. And after that, we identify two regions, the blue region and the green region. So in the blue region, the probability of observing at least one point source is larger than 90%. In the green region, the probability of observing at least one source is smaller than 10%. So you can think of them as simply a region of likely discovery, a region of very unlikely discovery. And I guess the first thing that one notices is that for steady state sources, which are shown here, the green region occupies most of the plane. So that means that most of the candidates are not leading likely to a point source discovery. That means that if we discover something, it will be surprising, and we will be able to exclude a lot of these sources as dominant candidates to the neutrino sky. On the other hand, the blue region still has a few candidates in terms of density that could saturate the diffuse neutrino flux and contemporaneously lead to a detection. This is the case for flat spectrum radio quasar. I've already mentioned them before because they are particularly bright sources, so they could in principle have a large neutrino flux individually. Okay, that was just the bottom line. I've already told that. So I think I can just skip to my conclusions at this point. I think the main message I wanted to send is that ultra high energy neutrinos are important astrophysical pointers to ultra high energy cosmic ray acceleration, which we could otherwise not probe directly or indirectly. Okay, so this was more or less the bottom line on the first part of my talk. I've also mentioned beyond the sun physics of the motivation, but I didn't spend much time on this. Although there are works in this direction, it's certainly interesting, but it's kind of a secondary interest. The other conclusion that I wanted to give is that we must learn to make good use of the observables that we will have available if measurements should be done. These observables, I think, just as in the ice cube range, are energy spectrum, angular distribution, and flavor composition. Energy spectrum, I mean, there are some works in this direction, but again, I think one should really work and try to understand whether there are some simple observables that could be used to discriminate different models, which at present I'm not aware of. In a simple way, angular distribution would be an ideal probe of point sources because you can look for clustering of neutrinos, which would be like a direct identifier of point sources. There are other ways in which you could use angular distribution, for example, to discriminate non-standard scenarios of production, but I just didn't have time to go into that. I also want to emphasize that the multiplet method that I have applied for this talk is kind of a blind method, right? We were only looking at the neutrino sky and we were seeing if we were seeing clustering. In reality, we have additional information. We have multi-messenger correlation. Probably the ultra-high energy neutrino point sources that we will be able to detect will actually be discovered not by just looking blindly at the neutrino sky, but by correlating with, for example, gamma ray signal, or with catalogs of known sources like lasers and something, or gamma ray bursts or other things. So I think it's important to keep in mind that the multiplet technique is just one technique, but we have to make the most use of the multi-messenger correlation to really show information about that. And yeah, there's flavor composition, which I didn't have time to talk about. I kind of spoiled something at the beginning about the ground. If we are able to make good use of the interplay between ground, which is mostly sensitive to nu tau, and ice cube to radio array, which is instead kind of uniformly sensitive to all flavors, that could be a way to also get information on the flavor composition and learn something about the production mechanism. So that is kind of a complementary probe that still needs to be developed, and I think there is work in this direction already. So I think that's all from my side.
So I have a question. So the diagonal that you showed in your so this is this intermediate flux that you showed. So if you have a discovery of so this is the blue region is the non-discovery of the sources in radio. Would you then not also be able to construct the source by PEV origin, or do you consider a flux which is falling towards the PEV that is basically undiscovered?
Yeah, I mean, so you're talking about whether we could do something with ice cube as well.
Yeah, in combination.
Yeah, I mean, I guess you could do it if you have a specific prediction for the spectral shape. Of course, this was a paper in which we were mostly blind to any kind of model-dependent prediction, so we didn't want to have specific predictions for the spectral shape. If you have a sufficiently heavy tail in the PEV range, ice cube could be a complementary probe, possibly more powerful depending on how the spectrum is shaped. Yeah.
Because in 20 years, we have a lot more data, right?
Yeah, I agree.
Do you have questions?
If I understood correctly, you said that searching for multiplets of high neutrinos could distinguish between like having source neutrinos or having cosmogenic neutrinos. I don't really understand if you have a source that is accelerating cosmic rays and shooting them, of course the neutrinos are coming from the source, but shooting the cosmogenic neutrinos also will go into the source.
No, yeah, you're right. I mean, what I was referring to is cosmogenic neutrinos produced by the cosmic rays that we observe at Earth, like say within the GCQ horizon. Those will not be correlated with a specific extragalactic source, right? Because they are interacting in the intergalactic space. But I agree. I mean, yes, if cosmogenic neutrinos are produced locally, let's say in the GCQ horizon of the source where they were produced, yes, they would look like source neutrinos. They will also pass. So yes, I agree. That's correct. Great thing.
So the background here is the diffuse background. There is extreme energies you are not considering any cosmic ray backgrounds.
No.
Expertise. So this is should be.
Yeah, this is just a thing. There is like I think the cosmic ray background of Gen 2 is we estimated it to be subdominant compared to this. I mean, for sure compared to these fluxes, even when I'm referring to this intermediate diffuse between fluxes, we are still talking about something like 50 to 100 events in 10 years. So it's still quite a lot of events, and the cosmic ray discrimination then allows you to have a negligible compared to these numbers. Yeah.
Okay. Do you mean the cosmic rays or the millions?
So for this multiplet analysis, I understood you use the diffuse background as a background fluctuation from Poisson statistic, and then you have on top of that the neutrino sources, right? Yes.
Yeah, I think
So, but I mean, I could imagine that there are also other backgrounds.
like misreconstructed cosmic rays, right?
Yeah.
Yeah, I agree. I mean, because I think Marisha was talking about atmospheric muons, and atmospheric muons are really negligible. So it's like 0.1 event, right? 0.1 event in 10 years, I think, if I remember the number correctly, something like that. There is also cosmic ray misidentification, which is not completely estimated, I think, because it also comes from reflected showers. So I don't think there's a very good estimate, but the estimate that we were able to track from Christian and other people in the collaboration were much lower compared to the event rate that we were using here.
And so thanks. What exactly makes RAM more sensitive to tau neutrinos? Can you?
Yeah. Okay. Let me just go back. Okay, I'll just do it right now. Yeah. So you mean why this process can only happen to tau neutrinos and not to other things? Yeah. So yeah, it's simple. So if you had an electron neutrino, the first electrons are much more interacting than tau because they are much lighter. They would just be stopped in the rock immediately. And that's actually also the case for the muon. So the energy losses are just too strong. They would be stopped in the rock before exiting and therefore producing something in the atmosphere. The tau has a kind of compromise between a decay length that at those energies is long enough to reach the atmosphere, because if it were too short, it would decay inside. But because of relativistic boosting, these are very high energy, so it's large enough that it could enter the atmosphere without losing too much energy. So it's mostly connected with the mass of the tau lepton.
Okay, the question, thank Damiano again.